Hi, this is Saxman. I did a panel on FM synthesis back in August 2024, and needless to say, it didn't quite go according to plan. We started 10 minutes late, had some technical issues, and just ran out of time at the end. I was a little disappointed, but we did film it, and I decided rather than waste that footage, I would just go ahead and release it as is. Because there really is a lot of good content there that I think people could benefit from. So we're releasing it now, and basically what it was, I wanted to show the relationships between Yamaha FM synthesizers and a Sega Genesis and other video game platforms, because those chips are very closely related. I grew up around FM synthesis. I have a couple FM synthesizers right in front of me. These used to belong to my dad back in the 80s and 90s. Toward the late 90s or early 2000s, he, more or less gave them to me. Not officially, but I've had them ever since. One's a DX72 FD, and the other is a TX81Z. Well, the TX81Z is a 4-operator, 8-algorithm synthesizer. That's the one that is very closely tied to these games. I have a long history of working with FM synthesizers, about 25 years roughly. I used to hack Sonic ROMs, and back when nobody really knew anything about them. And one of the areas I did was the music. Long story short, I discovered that the data in the Sonic games was very, very close to, characteristically to what you could do with the TX81Z. And I ended up documenting the format of the voice data along with the sequence and different things like that. But I've been fascinated with them ever since. And I wanted to take that knowledge, do a presentation on how to create FM sounds, sort of the base knowledge that you would need to do that. And then to demonstrate taking an FM sound, a voice from FM synthesizer, put it into a Genesis game, and vice versa. We didn't get to all that. But I hope maybe to do that in the future. So I'm thinking about it. But anyway, big thanks to Andy Wolan. We didn't do a ton of editing, but he did do some editing that was probably very vital to, especially to the slides in the footage, to make them more visible, easier to see. So big thanks to him for all of his efforts there. And I guess without further ado, here's what we got.
Okay.
Yay, all right. So, my name is Saxman. That's what people call me on the internet. I have a real name. That's my damn business. But I'm going to wait for the panel to be over and the camera's off. I'll be happy to introduce myself properly. This guy here, I've known for 20-something years. Is SSN Tales. Might know him as co-creator of a little game called Sonic ROM Blast 2. So
I'm just here for the color commentary.
First of all, how many of you all are know anything about FM synthesis? Okay. Let me narrow that down a little bit, or broaden it rather. How many people know what FM is? Frequency modulation. Yeah, good. Okay. So I'm going to go over some of the sort of core concepts of FM, because this is going to help us later when we actually construct some of these voices and later port them over. I want to port, I have a TX81Z synthesizer here. I want to take some sounds off of this and put it in a Genesis gate. And then I want to do the reverse. So there's really four main things here. Can you expand this? Yeah. One. So there's really four main concepts about FM that you really should know. There's these two most basic components, an oscillator and an envelope. So an oscillator is just the thing that produces a tone. Your wall outlet is AC current. That's what this oscillator is doing. It's just an electrical signal that's pulsating a sine wave. And then you have, on the opposite end, an envelope. And that's simply controlling the volume of any signal you put in. When you combine both of these together, you get what's called an operator. And then an algorithm is the fourth component. That just is a chains a bunch of operators together. Okay? So let me move into what these operators do. So there's two types of operators. There's a carrier and a modulator. Carrier is what you're hearing. It is plugged to the output of whatever you're playing through. So it's the sound. The modulator is a type of operator that feeds into any other operator. It could be a carrier or it could be a modulator. But it's going to manipulate that signal. And I'll get into that here next slide. So this is, I don't know how well you can see that back there, but this is a modulator here. Modulator is feeding into a carrier wave, and the resulting output is this crazy looking thing with all these little tight waves and then these big bands here, tight, big band. That's what you're going to hear.
And one other way you can sort of think about it too is like with the clock signal, and that the modulator is modifying that wave that comes out from the oscillator. So it's like either speeding up the clock or slowing the clock down.
Yes, exactly. So this is the envelope generator. So the envelope is going to, this is just a change in volume. When you strike a piano key, it goes bing, and it sustains there. That's your sustain, that's when it's getting softer. This is the initial hammer coming down, and then it comes down sharply here, and then sustains. You release the key, the volume drops down to 0. Okay? Are you with me so far? Okay, excellent. Only thing you really need to know, Yamaha FM chips have, there's a whole variety, but the ones that have 4 operators on them, which is a lot of them, which is what you hear in a lot of video games, they have a standard set of 8 algorithms. And all the algorithm is doing is deciding how the order in which the operators are fed. And depending on the order can radically change the sound. So, there's really more text here than you really need. There's two, and this is key to everything. There's 2 main drivers of modulation. There's the frequency and the output, or the volume of that modulator wave. So the frequency is, what he was saying, is like what do you call it? Like
the clock signal.
Yeah, it's like a clock. And you're changing, basically, it's like changing a clock to shift the carrier wave. And I'll be able to show you this with a live demo here in a moment. So that just shifts the phase of the carrier wave. And then the output is just going to change the intensity of the modulation. Okay. So here are some examples of how this works. Over there, going up is a change in frequency. So if your frequency down here is 100%, 150, 200. On the other axis, I have modulator volume or output, and that's just increasing, starting at 0, 50, 100. Now, do I have a little more slack here? Hope you all can see this. If the modulator has no volume, it's not going to impact the carrier wave at all. What you're seeing here is just a raw carrier signal. When you increase, the frequency hasn't been touched, but when you increase the output here, you're getting more waves here, and then you increase it more, you're getting even more waves. I want you to notice, though, these two fat bands here, there's one up and one down. There's also one up and one down here. The only thing that changed was these smaller ones. We went from 50% to 100% output. You're doubling the number of smaller waves. The opposite is true when you increase the frequency. You have 100%, let's check this one, going up. 100% frequency, one up, one down of the fat waves. When you go to 200%, you have two of these up and two of these down. 150 is sort of the weird one that has one up, one down, and this one that can't decide what it wants to do. Is that making sense so far? I'm going to be able to show you this in real time. Now, how this works. A modulator, really technically a modulator is based on hypotenuse, but I like to represent as amplitude because I think it's easier to understand. When the modulator, say the modulator is 90 degrees that way, in other words, this high point is up here, the carrier wave is down here. So what's going on is the modulator is at its strongest here. As it comes down, this thing is starting to slow down because the modulator is changing phases. So this, as this signal goes down, this carrier wave is moving slower and slower. And so these bands are getting wider and wider until this hits 0. At which point, this thing stops. And then it starts going the other way. And it's going to increase the intensity some more, but it's mirrored. When the modulator signal goes negative, it actually starts phasing this in the reverse direction. And have that now. Now I just got to get my program up here.
That's effectively a multiplication operation, right? So that's why you get from negative to get the inverse.
Yep, that is exactly right. It is doing a multiplication. So I wrote this handy tool, I don't know, maybe 13, 14 years ago. Okay, I'll duplicate.
We know how to tell.
Hey. Awesome, thank you. Okay, so now you see this guy, and I'm going to put, where is it? This one down. Okay. So ignore this guy. This is two modulators and a carrier. This modulator is broken. These are only two we care about. I don't know how well you can see back there, but I'll just kind of guide you through it. So when I can enable and disable the modulator here, F5. So that's all you're seeing there is the carrier.
When I turn the modulator on, that's what you see. So, let me turn the volume down in the modulator, and then we'll re-enable it. So, 8, now re-enable. Okay, modulator's on, but the carrier wave is completely unaffected. Now I'm going to slowly turn up this volume. Now I want you to notice that little shelf there. When we produce a sound, that will come in handy. But as I increase the volume of this modulator, it's pushing out. It's almost like a line that's growing in length, except it's tethered here, it's tethered there. It's never, that part is never going to change. But I can increase the volume and do that craziness. I can also, and let me just do that, and then I'm going to change, we were changing volume. I'm going to change the frequency of this. I told you when the frequency changes, you get more of those fat bands there. Whoops, I have to change more of that. Let me zoom in. Sorry, hold on a second. You got to see more of this to understand this. Okay, so that's just the carrier wave, it's just kind of squished down. But when I increase the frequency here, let's bring this up to 1. Let's put close to 1. Now, let's strengthen the volume here. There you go. That's what you're talking about. So you got the one big band and one small. Now let's increase the thing, the frequency to 2. You notice as I increase this, those bigger bands keep popping up. You've got one here, 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 here. Because really, these are the points in which the phasing shifts. Remember I told you as a modulator crosses a certain threshold, when it hits 0, the direction of the phasing starts going the other way. That's what's happening here. This is a change in direction. And that's because our frequency of our modulator is much higher. And so it's happening more, it's happening more frequently. Let's see. Let me go back to the slides here for a second. Any questions so far? Makes sense. All right.
I got a question.
So, oh yeah.
Yeah. When you're saying frequency, are you talking about the frequency in terms of the tone that it's going to produce, or is it more about the frequency in, I'm trying to think of the right terminology? Are we talking about two separate frequencies here? One, the perceived musical tone, and one dealing with how the actual waveform is generated, or is it just one frequency? Say again?
You mean like the sample rate?
No, not the sample rate, the actual frequency of the note that our ear is going to perceive as being a musical note.
So, actually, well, I don't know if this might answer your question. Let me turn this frequency down. This is the when I say frequency modulator, I'm talking about the physical frequency, the sine wave frequency itself.
Okay.
So
that will affect the musical tone, or like the musical note that we hear. For some values of musical note.
Well, I mean, the more stretched out the waveform is, the lower frequency you're going, the lower tone you're going to hear.
Right. Yeah. it does give you sort of a perceived increase in
the pitch, I guess you could
pitch,
say,
I would
right?
say.
Yeah.
So are you adjusting the modulator frequency right now?
Yes,
Okay.
this is the modulator. Oh, well, that is horribly out of tune, but if I bump that up a little bit, it would be perfect pitch. Let's see, get it at 0. Right there. That's a perfect pitch. It's perfectly in sync.
You made your own PC speaker.
Yeah, that's it. So I don't know if that answers your question or kind of gives you an idea.
Yeah.
Is that just pure software right now, or is that a thing?
That's software. Yeah, that's something I wrote many years ago. I just dug it out for this presentation. That's actually mimicking the exact behavior of the TX81Z, which I have over this laptop here.
That's why I saw that, I was wondering, like,
Yeah.
which recording it, or if you were actually, like, obviously this context.
Right, yeah.
So if you were to set those same parameters on the X7, it would generate that same tone.
Yeah.
Yes. Yes.
Would you be just use a microphone and just draw that same sine wave essentially? I'm sure. Like if you're using recording software?
Say that again? I didn't catch it.
Like if you were using the real one essentially, and you had that cut to a speaker, you'd still be able to draw the same sine waves to get those values, just like you would on any recording software. I'm sure.
Yeah. Yeah, you should be able to. So I asked myself, well, do you want to dive into all this history? I don't want to, decided it was too much, but I do want to just highlight sort of the origins of this synthesis here. So that is Yamaha's very first FM synthesizer, that being the GS1, released in 1981. It was prohibitively expensive, and so there's not a lot of them out there. But in 1983, we got this DX7 alongside the DX1 and DX5. But it's the DX7 that was that was the first affordable FM synthesizer, and I'm sure anyone who's read anything on FM synthesis knows that thing was a monster back in the 80s. Yamaha produced a lot of FM chips, lots and lots of them, many different classes, like the OPL, they call it operator type L. I don't know where you get the letters, but OPL chips were used in some sound cards. The Sound Blaster had one of the OPL chips. The Mark III, Sega Mark III in Japan. I don't know if it came with an FM chip or if it was an add-on, but
There was an add-on for the SC3000.
okay, that's what it was. The OPN family, there's OPN, OPN2, OPN-A, OPN-B, OPN2L, OPN3. I can't even tell you everything about all of them, but the OPN2 is from the Sega Genesis, and that's what we're going to use today. Just briefly, the OPM, that's probably the most famous one because a million arcade games used it along with certain computers. And then Yamaha's own FM synthesizers, the ones that are 4-operator based, tended to use the OPP or OPZ or even OPZ2. The OPZ was sort of an upgrade. Well, the OPP is actually the OPM with expanded test register. Otherwise, it's the same. But the OPZ added some extra functions. So you could select different types of waveforms other than sine. So you do sawtooth, triangle, all that stuff. And then OPZ, oh yeah, and then fixed frequencies. So for like sound effects, if you wanted to just set the operator to an exact frequency. And then OPZ2 just modifies the range of those frequencies. So there's, obviously you can see a whole line of Yamaha synthesizers that use these. It's just a bunch of them. The TX81Z here actually uses the OPZ. That's where it gets its name. I don't know, this is too much. That's just a bunch of chips. Where's the part numbers? Okay. Oh yeah, okay. You know, if you have a phone, if you care, there's just some links I thought was useful to have if you want to learn more. But
Are you gonna post these slides?
yes, I will make these available. And I guess there'll be video too, won't there, Andy? Yeah. Let me, because I got this box going down here, I want to try and create a voice. In the time we have, if I can do it.
Have you messed around with trackers like Furnace at all? Is this sort of setting up the sounds similar in that environment? Do you know?
Trackers, yeah, you can, well, I shouldn't jump the gun. Certainly, I know trackers can sequence the notes. I don't know if they get too much into actually constructing the sounds or not. I don't know. I know you can import a lot of them. Oh, you can't see my thing.
Maybe it's unduplicated.
Okay.
PowerPoint might be getting in the way of that.
Okay, let me close this. Does that? Okay, good. Now you can see the screen. So, what I want to do, and since we're tight on time, I have a cheat sheet to get through this, so I can demonstrate why some of those things I mentioned were important, particularly the frequency and output. So I want to replicate a piano. And to do that, let's see if I can do this on time, in a timely manner. I want you to be able to see what the heck I'm doing here. So, in OBS. Okay, that's probably good enough. I hope.
How do you focus with this? With this, you know, with this?
Yeah, there you go.
I can be a little bit of a camera.
Yeah, that's very helpful. Thank you. All right, so I want to start with a blank slate here. So I'm going to move over to something completely blank. Edit voice. I think that's a blank slate. So, first we have, we're going to go, so this is the algorithm. Oh, yeah, you got to this. Nope, here. Yeah, there you go. Yeah, I don't care about buttons.
Okay.
They can see that. So that's your algorithm. So I'm fine with one. I remember what one is.
One thing that kind of helped me think of algorithms is sort of like, imagine you have a preset way that you can chain together GPU shaders. You know, you've got a certain number of shaders and you can combine them in different ways.
So all this algorithm is doing, one is just the sound, that's the carrier wave. And then you have 3 modulators chained together in sequence. So you always want to start with just a carrier and a modulator. And then you get more sophisticated from there. So So let's go to the next parameter, feedback 0. We don't want to do any of that. LFO, I'm going to turn that daggone thing down because we don't need that. Yeah, get rid of that. Nobody cares about that. What is that even in? The blank slate. Sensitivity. Okay, just making sure these are down. Okay, edit frequency. So we can set the frequency of each operator here. So, course frequency. So, these are ratios basically. This is a 1. And then our modulator. So, this is operator 1. When I go over here, we have operator 2. So I want, I'm fine with them being the same.
And those values can only go from -1 to +1, correct? Or can you actually exceed?
No, so these are actually based on 1. You're thinking of the volume. Yes. Let me show you a picture of what I'm actually doing here. So this is a piano. This is a real piano. Notice the structure here. Goes up, crosses this threshold, comes down. But when I talked about the shelf earlier, how it kind of went up here like this and then leveled off before it dipped down again, you kind of see that same thing here. Because this is real tight here, but it ends up crossing over here. So that's one thing that I noticed when I looked at this. The other thing is, remember how when you change the number of, the frequency of the modulator, you get those the big number of big humps there changes. If you can think of this as a sine wave with a bunch of little humps on it, this is like 1, 2, sort of 3, 4, 5, 6, 7. It's hard to kind of get it exact, but that's an approximation. Say 7 humps you can really visually see there. So what I'm explaining to you is that can be your modulators. So if I take operator 2, which is our modulator, let's use algorithm 3. This will be easier. Look, I'm using algorithm 3 here. Let's go back to OBS so you can see what the heck I'm doing here. There's a focus. Perfect. So I'm switching to algorithm 3. This is going to be easier. So 1, 2, 3. Now I want to go over.
Oh, you're going to need to go back to the.
Because I also want to show them an oscilloscope here.
You don't have to close the projector thing, you can just alt tab to it, by the way, if it's in the window.
Oh, I can. Where OBS?
So, yeah.
Okay, so I can still do that.
Yeah, if you right click the projector thing, just do the ag, bring it up again. Just use alt tab.
Alt
Just
tab.
choose OBS, just make that.
Okay, perfect. Thank you.
Just use alt tab, that way you're not worried about closing it over that. You're at 250 right now.
Oh, 250. Daggone. Okay, so let's get this one here. Oh, this needs to be on. Do we have a signal? Perfect. Thank you. So we can see what we're doing here. Now I want to increase frequency to match. this thing here. So we're going to do frequency of 1.
So I guess kind of what they used to do to try to simulate real instruments is they probably recorded the actual instrument playing the sound, looked at the shape of the waveform, right?
Yeah.
And then they thought of like, okay, what algorithms and how can I combine the modulators and the operators together to get as close as I can to that shape of the waveform.
That's what I was asking earlier, recording the software.
Yeah.
More commonly, they would use a spectrogram, so they'd see the harmonics from that instrument, and they try to make the harmonics line up reasonably well from FM output. Anyways,
Oh, yeah, that's true. Yeah, I forgot about that. Yeah. You can use a spectrogram.
yeah. It's pretty hard for humans to interpret complex waveforms, but spectrograms, you take the first 3 or 4 harmonics and you get them good.
So here we go. So I'm going to increase the modulator, switch over to
Back to
studio.
zero.
Yeah. So I want to get 7 of those waves. So let's.
The job title of someone doing that, like sound engineer.
Sound designer.
Yeah. It's really not the actual name like these.
It's not composer, right?
Right, probably, yeah, that's the one I'm using.
I know that some composers, like such as Howard Drossen at Sega, he never actually did any FM programming, I don't think. Like he would use the GEM sound driver and then just, feed his music into that. So I mean,
Oh, jeez.
it's quality may vary, but it's made it a little bit more approachable for musicians.
It goes the other way too, right? Like Yuzo Koshiro famously, like he would just get into
What's that?
Koshiro, I think he would like dive into the design as well.
Oh yeah, I'm sure there's musicians who did that too.
So you see that? See that little shelf there? That's what we want. You go back here, do that thing there. See, my first operator is just a carrier, but the second operator I've turned it up to 61. It goes up to 99. So at a volume of 61, I get that little shelf. The frequency is exactly the same. So now I want to set up the frequency of the third operator, and we want those little humps that I said, that I pointed to. So operator 3, there were 7 humps as I counted. So I want to make the frequency a multiple of 7. And now, when I go over here, and I'm going to be increasing the volume of this, but
Yeah, I can hear the piano a little bit.
Quick and dirty piano.
yeah. And then we can get an envelope generator on these to shape the volume. So, how much time we got? Oh, 55.
Yeah, we probably don't have enough time to do envelopes.
Okay.
But what you would probably do is like for the velocity of the note, you would increase or adjust the envelope. So like the faster the velocity,
Well,
the faster the note.
I'll tell you what, I didn't have enough time to port the voices, but we're at the Headcannon booth. I'd be more than happy to show you all how it's done. I could do it right there. I'm sorry I didn't have enough time to do it here. We just got started too late, and technical problems. But are there any questions while you have me up here? Sure.
I want to have a sort of question where it's like, what if, I'm looking at you're creating the waves. I assume all those chips
Yes.
should basically create these waves and make these tones.
Right.
So then, when I fire up my Sega Genesis 2 with the 2612 or whatever, and the Genesis 1 with the 38, whatever the name of the chip is, they just have a slightly different sound. Like, What did Yamaha like change there? Was it just cost cutting or what was it?
They actually, a lot of the tones will sound exactly the same. What's different, like the TX81Z, the OPZ chip, has a lot of additional parameters. I can't think of what they are right off the top of my head, but there's a bunch of additional parameters that they have. But they both have 4 operators, the same 8 algorithms. You can tune the frequencies the same. The frequency range on the TX81Z is greater, so it's a little more granular. Has several LFOs, whereas the Genesis just has 1 LFO. LFO, no, it's a low frequency oscillator, so it kind of oscillates the entire sound as opposed to a single operator. But a lot of the sounds will sound identical. That's what I was hoping that I had enough time to show you, that I could take this, put it into a Genesis game, and you'd hear the exact same thing. And I can take any sound from any Genesis game and move it over here, and there's almost a guarantee that it's going to sound exactly the same. In fact, one of these over here, I have a couple of these loaded here. Oh, there we go. I don't know what's in there. I think that's the bass in Sonic 3. The launch bass.
Okay.
So it sounds, it's identical. But yeah. So again, if you want me to demonstrate some voice porting, I'd be more than happy to do it for anybody who wants to come over to the Headcannon booth. Also, we have 2 panels tomorrow, I want to say. We have the Doom World Building
At 1 o'clock.
At 1 o'clock, and we have the Headcannon panel at 2, is it?
Yeah, so the 1 o'clock panel is going to be right here in this room, and it's going to be covering the basics of getting, it's like a crash course on building levels for Doom. If you've never done that before, getting you started. And then over in the other panel room, right after that one, Headcannon's doing theirs at 2 o'clock.
All right. I hope you all will come by, but if not, thank you all for coming out, and that's okay, you know.
I'm trying to think about how to apply that. So I think you could.
Try to cover a lot.
Can you all hear me?
Yes.
Yes.
Hey.